Section 5.5. In this lecture, I've actually combined ideas from sections 5.4 and 5.5 in our textbook. Section 4 in our book is primarily dedicated to introducing notation for representing a system of differential equations. Then 5.5 derives the main idea that's at the core of our technique for solving systems. I've put all of that together in this lecture. So the first thing to point out is the scope of this chapter. We're talking about systems of differential equations, but exactly what type of differential equations will be involved in our systems. We'll actually have a pretty limited scope here. We'll be looking at systems containing first order linear differential equations. And when I say first order and linear, I mean exactly what you think I mean, the same definitions for order and linear that we've used all semester. And here I've provided a few examples of systems comprised of first order linear ODEs. A quick reminder that I'm thinking of x sub 1 and x sub 2 as dependent variables, functions of t. And so x1 prime and x2 prime are their derivatives. So in this first system, the derivative of the first function is dependent on the first function itself as well as the second function. So x1 prime is equal to 4x1 plus 2x2. Similarly, the derivative for x2 is defined in terms of both functions. And remember that each of these, x1 and x2, is a function of time. Notice also that these last two systems contain not only x and x prime terms, but also terms like sine of t, t squared down here, etc. In chapter 3, we introduced the distinction between homogeneous and non-homogeneous differential equations. That distinction remains in place here. A system in which only dependent variable and derivative terms, x and x prime terms, occur is called homogeneous. A system like these last two that contains terms that are functions of the independent variable t are called non-homogeneous. And actually, most of what we do in this chapter, the assumptions that we make about the form of solutions, our method for building solutions, etc., will be borrowed or sort of recycled from chapter 3. You'll hopefully see what I mean as we work through this lecture. And this makes sense because if we look at a simple example of a system, say the first one from the examples above, what each differential equation is telling us pretty clearly suggests that we should do chapter 3 type things. Here's what I mean. Look at this first equation. It says that the derivative of x1 is 4 times x1 plus 2 times x2. So what types of functions could satisfy that relationship? It actually seems like maybe a pair of polynomial functions could satisfy that relationship. Imagine x1 was a quadratic, so then x1 prime would be linear, and then maybe somehow x2 could balance those out so that everything works out. Try it. See if you can come up with, say, quadratic functions that work in this system. I actually tried it briefly. I didn't put that much effort into it, but I wasn't able to come up with a way to make it work. But maybe you can. Try it and let me know if you can make it work. So polynomials seem like they might work, but actually the prime candidates for solutions are going to be exactly the same types of functions that we had as solutions in chapter 3. Exponentials, maybe sines and cosines, maybe exponentials times sines and cosines. But those are really the main candidates. Again, think about this first equation. If x1 is an exponential, then I could clearly imagine suppose x2 is also an exponential. I mean, suppose they're even the same exponential, e to the 2t, for example, then I could clearly imagine those two functions summing to equal the derivative of x1 because this derivative will itself be an exponential. So with that in mind, let's do what we did in chapter 3. Let's assume our solutions have a certain form, plug the necessary ingredients into our differential equations, plural, and see if we can make sense of what comes out. I'm going to go full chapter 3 here and assume that both functions x1 and x2 have the form e to the rt. but I don't actually think that both functions will be the exact same e to the RT. So what I'll actually do is give them their own coefficients. So I'll assume that x1 is gamma sub 1 e to the RT, and x2 is gamma sub 2 e to the RT, where gamma 1 and gamma 2 are some unknown constants at this point. So let's look at that first example. There is a typo here, that 3. So let's look at this first system and see what happens if we plug in these assumed solutions. Quick forewarning, the notation on these gets a little overwhelming. So hopefully you can track with me as I work through this, and please go back and review and kind of work through step by step just to double check you're clear on what's going on. So my original system, in the first equation, it says x prime equals 4x sub 1 plus 2x sub 2. I'm assuming that x sub 1 is gamma 1 e to the RT. So its derivative will be r gamma 1 e to the RT. So when I differentiate, I just have to apply the chain rule, and that r comes out front. And then here in the rest of the equation, I've simply plugged x1 and x2 in directly. In the second equation, x2 prime needs to be 3x1 minus x2. So here is x2 prime. Once again, I just have this extra r that comes out front. And then here's 3x1 minus x2. Looking through both of these equations, I know that e to the RT is never 0. And there is an e to the RT term in every single component. So since that term is non-zero, I'm free to divide through by that. And that leaves me with this system over here. So if I look at what's going on here, I've got r gamma 1 equals 4 gamma 1 plus 2 gamma 2. And then a similar equation here in this second equation. So I plugged in my assumed solutions, and I have this algebraic system here. At this point in chapter 3, I had the characteristic polynomial, which we could readily solve for r. Here, not surprisingly, I have a system instead. So can I solve this system for r? I guess I actually need to solve not only for r, but also for gamma 1 and gamma 2. And that's kind of a problem, because that means we have 3 unknowns, r and the 2 gammas, so 3 variables, but we only have 2 equations. Is there some fancy algebra we could utilize here to solve for all 3 variables? Well, it turns out that in order to see how to solve for these variables, the r and the gammas, it will be helpful if we introduce slightly different notation to represent all of the ingredients in this problem. And bear with me here, this is where I admit the notation gets a little intense. So just one detail to keep an eye out for, I'm dealing with scalar quantities, like numbers, like regular numbers, like the coefficients, the 4, the 2, the numbers. But then I'm also dealing with vectors, and I'm also dealing with matrices. Actually, one matrix, as you'll see. So maybe a tip here is to keep a close eye on what's a number, what's a vector, what's a matrix, etc. Anyway, to start, I have these 2 solution functions, x1 and x2, which we have assumed are the functions gamma 1 e to the RT and gamma 2 e to the RT, respectively. If I wanted to, I can sort of quote-unquote hold these individual functions in a vector like this. So here my first component of the vector is x1, and the second component of the vector is x2. So this x vector I think of as the solution vector. And then I can manipulate this particular solution vector a little bit. First, I note that there's e to the RT in each component. So if I wanted to, I could actually factor out that e to the RT. So now we're saying that our solution vector x is this gamma. Well, I guess this gamma is like a gamma vector times e to the RT. And so if I wanted to be even more concise, this gamma here, where I've got gamma 1 and gamma 2 as the 2 components, I could actually name that its own vector. And so in terms of the notation, this is pretty concise, but I could actually write that I believe my solutions have this form here. So I'll write the vector x equals the vector gamma e to the RT. And maybe you can, just for reference, kind of work backwards through this paragraph to see like a different sort of fuller version of that solution vector if this concise notation is a little confusing. Then if my solutions are held in a vector, it's natural to hold my derivatives in a vector. And once again, I could kind of build them in a real explicit way where I've got each derivative as a component of a vector. Or borrowing this vector, factoring out what I can eventually write x prime simply as gamma r e to the rt, where x and gamma are, of course, vectors. And then the final ingredient would simply be the coefficient matrix. So from the example that we've been working with, my coefficient matrix would look something like this, but more generically, I would just think of it as some square matrix, some square coefficient matrix, capital A. Then, now make sure you're clear on this structure, but then using these ingredients, I can write our original system as simply x prime equals ax. So this x prime vector holds x1 prime and x2 prime as its individual components. This x vector holds those dependent variable x1, x2, and then capital A holds the coefficients that are specific to that problem. And so this tiny little equation here represents the entire system of differential equations. So remember that the point of all of this notation is to figure out how we're going to solve for R and the gammas. The core idea shows itself pretty directly if we just use this notation. Let's take a look. So just as a reminder, my entire system can be written very concisely as x vector prime equals a times x vector. And I actually point out below that one major advantage of this notation is that it doesn't put any sort of restriction on the number of dependent variables. So in the example that we have been working with, this x vector holds x1 and x2. But if I wanted to have a 3 equation system and I needed 3 dependent variables, x1, x2, and x3, I could represent them as a solution vector like this just as easily. So this simple representation here actually represents systems of differential equations that have any number of dependent variables. Now remember, we want to assume that x has this structure here, and that tells us that the derivative will have this structure here. And so I can go into my system and make those substitutions. So let's see how that plays out. Instead of the original system, x prime equals ax, I'll have this system here. The gamma r e to the rt is the x prime vector. And then I have the coefficient matrix A, and then this gamma e to the rt is the x vector. Once again, I have an equation where there's an e to the rt on both sides. E to the rt is never 0, so I can divide by that, and that leaves me simply with this equation right here. Now, here's the punchline. If I take this equation and just rewrite things in a slightly different way, it says a times the vector lambda equals r times the vector lambda. And this equation right here is the eigenequation. So in section 5.3, when we spent all of that time practicing how to find the eigenvectors and eigenvalues of a given square matrix, here is where that ties into solving this system of differential equations. So as it says here, my goal was to find the gammas, but also to find R. And this derivation here indicates that the R and the gamma will be an eigenvalue eigenvector pair for my matrix A. So in order to solve a system of differential equations, it boils down to finding the eigenvalues and eigenvectors of the coefficient matrix. That's a really, really important idea, so it's worth restating. The central idea here is that to solve a system of first-order linear homogeneous differential equations, which we've represented very concisely here, to solve that system, we find the eigenvalues and eigenvectors of the coefficient matrix, then use those ingredients to build our solution in an appropriate way. Now, I have a feeling that build your solution in an appropriate way will actually require us to account for these different cases. Remember, we're solving for eigenvalues, so all of the usual possibilities could occur. We could have distinct eigenvalues, repeated eigenvalue, or we could have complex eigenvalues. We've actually seen each of these cases in recent examples and homework problems, so I'm sure we'll have to account for these different cases. And that's actually what the next couple of sections address. And then I expect that we'll borrow from chapter 3 further by building a general solution using this sort of linear combination approach if I have distinct eigenvalues, say R1 and R2. So our textbook actually ends at this point. It just describes this important result and then it wraps it up without ever working a single example. I want to do at least one example to see how all this all plays out. So let's go ahead and actually solve this example system that we've been pointing to throughout this lecture. So first, in a sort of fundamental or preliminary way, I'm just defining all of these ingredients. X prime will be the vector that holds these derivatives on the left-hand side, and then I'll have my coefficient matrix A, and then the variable or solution matrix X. So this system really can be written as X prime equals AX, as we pointed out earlier. And now, to enact the method that we just described, I'm going to suppose that my solution is actually an exponential function with individual coefficients on each of the components. So x1 is equal to gamma 1 e to the rt, and x2 is equal to gamma 2 e to the rt. That, of course, implies that x prime, the vector x prime, will equal this same coefficient vector, because when I take a derivative, the coefficient is unaffected. And as always, when I differentiate e to the rt, I'll get r e to the rt. Now, plugging these into this system, I get an equation that looks like this here. So I have x prime equals a times x as dictated by the structure of my system. As always, it seems like I can cancel out this e to the rt, and then just to make this look more explicitly like my eigenequation, I'll write this in a slightly different way. This implies that my matrix A times the vector gamma, and here instead of writing it as just gamma vector, I'm writing it with its individual components. So A times gamma equals R times gamma. And this is all pretty much exactly what we just stated, but I'm just writing it out here just to kind of see it again and see exactly how these ingredients come together. So this is, of course, the eigenequation. A matrix times a vector equals some scalar times that same vector. So I can conclude that these two ingredients that I've got to track down, the R and the gamma vector, are exactly an eigenvector pair for my coefficient matrix A. So all of this in orange is kind of just a restatement of the basic derivation that we just did on the previous page. Let's go ahead and actually put this to use. So I need to start by finding the eigenvalues and eigenvectors of A. We got practice with this in the last section and recent homework. So here I've worked through those first preliminary steps for solving for the eigenvalues, lambda. I always start by solving the equation 0 equals the determinant of A minus lambda I. A minus lambda I know will just be my original matrix A, but with lambdas subtracted along the main diagonal. And then when I calculate that determinant, that turns this matrix into a polynomial. And here I've worked through the algebra, and it looks like I'm going to get two real distinct eigenvalues, namely lambda equals -2 and lambda equals 5. So I'm not done with all of my calculations yet, but just to quickly put those values into the context of this problem, remember we're assuming that my solution looks like e to the rt. And this is actually indicating that there are two r values, r equals -2, r equals 5, which will permit that exponential to work in this system. Knowing what that exponential isn't sufficient, because I also need to know what the associated coefficients need to be. So I'll need to find the eigenvectors, which are associated with these individual eigenvalues. Let's go ahead and give that a shot. So starting with lambda equals -2, for example, I will use the typical method for finding the corresponding eigenvector. I'll solve A minus -2i times a vector equals 0. I just want to point out, I can't really, in previous examples, certainly in 5.3, we were accustomed to using the vector x during this eigenvector calculation. It's really not a good idea to write the vector x here, because now in this problem the vector x means something specific, which is not exactly what it would mean here. Our book uses this variable. This is an eta. It kind of looks like an n that's sort of fancy, like a lowercase n that's got a bit of a tail on it. And then I get carried away and I'll sort of write it a little fancier. So I believe that this is an eta. So that's the variable that our textbook uses, so I'll go ahead and use that here. So setting up this system leads to the augmented matrix given here. And as with a lot of the previous examples, I'm not going to work through every detail when it comes to solving this system. In this particular case, I know that if I were to follow the necessary steps, this system would reduce down to this version here. And then from this first equation, again, if I think of the components of this eta vector as eta 1 and eta 2, then this first equation says 3 eta 1 plus eta 2 has to equal 0, from which I can quickly derive that eta 2 has to equal negative 3 eta 1. So my eta vector will have the structure. I can choose whatever I want for the first component, and then the second component will be negative 3 times that value. And as has been customary, I'm going to actually leave out those parameters eta 1, and I'll just write that my eigenvector in this case is 1, negative 3. And I have to be sure to keep those two ingredients sort of associated, tied together. This eigenvector is the eigenvector that is associated explicitly with lambda equals negative 2, that particular eigenvalue. My other eigenvalue is lambda equals 5, so I'll follow this same procedure, work through, find the corresponding eigenvector. So take a second to work through these details yourself and double check that I've done everything correctly here. But I believe that my eigenvector associated with the eigenvalue of 5 is given here, 2, 1. So now let's put these ingredients back into the context of this specific problem. So based on the assumptions that we made at the beginning of this process, the general solution of this system will have this structure here. I'll have exponential functions where the coefficient in the exponent is the eigenvalue, and then the coefficient vector on that exponential function will be the corresponding eigenvector. And in this case, since I have two distinct eigenvalues, I'll have two separate exponential functions that build my general solution. And so I'll have the two corresponding eigenvectors as appropriate. Putting in all these ingredients that I just calculated gives me this general solution here. So I have C1 times my first eigenvector, and then that's multiplied by e to the negative 2t. Why negative 2? Because that was the eigenvalue associated with this eigenvector. Fill in similar details here on this second component, and this is my general solution. In a certain sense, we're done with the problem, but I do want to point out that there's just a couple ways of rewriting this answer. And I think this is helpful sometimes just to remind ourselves of exactly what we're dealing with here. Remember that this vector x actually has two components. It's got an x1 in its first component, x2 in its second. And then these constants, this c1, along with this kind of constant function, can be pushed in to each component of these coefficient vectors. So if I think of this first vector, it actually has the structure c1 times 1 times e to the negative 2t. Similarly, the first component of this portion would look like c2 times 2 times e to the 5t. And so if I separate the two rows that exist in this vector expression, I actually get something like this. And this form of the solution is perfectly equivalent to this vector form. but I just kind of find it helpful to actually see explicitly what these functions are. Remember, we started by assuming that x sub 1 is a function of t, and we expected it to be built out of exponentials, and sure enough, I can see that x sub 1 is e to the negative 2t and e to the 5t with appropriate coefficients in front of those terms. These coefficients c1 and c2 I could of course solve for if I was provided with an initial condition for this system, but in this case we're not provided with such initial conditions, so we just leave our solution general. But as I said, I just find it helpful to kind of rewrite these individual functions here just to reiterate exactly what's going on. So that wraps up section 5.5. In the next couple sections, we're going to deal with the distinct cases for what can occur when it comes time to solve for the eigenvalues. These are our familiar cases of real distinct root, real repeated roots, or complex roots. So that's what we'll be looking at in the next couple sections.